All right, let's help our friend work on a statistics problem. So they go to a local NBA game and measure the heights of 20 players. They obtain an average of 81 inches and a standard deviation of 5.3. They then construct a 90% confidence interval about the true height of men. So we need to find this confidence interval. Let's start there. So let's write down the relevant information. The average height that they got from measuring 20 players is 81. The standard deviation that they measured was 5.3, and they measured 20 people, or rather 20 NBA players. So I want to construct a 90% confidence interval around the true average height. So I'm estimating an average using sample data. So I'm going to draw a normal distribution because I know by the central limit theorem that averages are distributed normally. I'm going to center my curve around my sample data of 81, right? That's the average that I got. And I'm going to remind myself, actually, we need to calculate a new standard deviation because the standard deviation of your sample is not the standard deviation of the averages. The standard deviation of your averages is given to you by the standard deviation of your sample divided by the square root of n. Right, that's given to us by the central limit theorem. So the standard deviation of your sample was 5.3. You measured 20 NBA players. The standard deviation of the averages is about 1.185 inches. So how far do I need to move over to collect 90% of my area, right? I'm trying to construct a 90% confidence interval. So how far do I need to move over there and how far do I move over there? So we need to find the margin of error. The margin of error is given to us by a critical value times the standard deviation. Now, we're going to choose t-scores for critical values because we're estimating averages. And our standard deviation is going to be the standard deviation of the averages. So the standard deviation of your sample divided by square root n. So we actually already know what that is. The standard deviation of the averages is 1.185, right, given to us by that number there. Now, what is the t-score? So I'm looking for the t-score that matches this picture right here. So if I have 90% in the middle, that means I have 10% in my two tails, or 5% over there, and 5% in that tail. Either way, the t-score that matches this picture is 1.729. So you can get that from your table. Just remember that your t-score critical value sheet uses degrees of freedom, and your degrees of freedom here is one less than your sample. So you're looking at degrees of freedom being 19. And if we multiply these two numbers, we find that a margin of error is about 2.049 inches. So that's how far I need to move over. If I take 81 and I subtract 2.049, I end up with a lower bound of 78.95 inches. So that's going to go right there. That's my lower bound. So this is 78.95 inches. Now, if I take 81 and I add that margin of error to find my upper bound, 2.049, I find an upper bound of 83.05 inches. So that's going to go right there. 83.05 inches. All right. So this is our 90% confidence interval. We are 90% sure that the true average height of NBA players is somewhere between 78.95 and 83.05. All right, but what's wrong with their claim? They have a flaw. They constructed a 90% confidence interval about the true height of men. So their claim is much more general than their study. They only studied 20 individuals at an NBA game, or rather 20 NBA players. So their height is probably going to be shifted significantly to the right, right? They're going to be taller than the average man. So they're better off making a conclusion that's about NBA players rather than all men. And our third question kind of points to that direction. If we want to sample, or rather, if we want to estimate the true average height of an NBA player to within 1 inch, how many people would we have to sample? So there, we just need to take this error equation and rearrange it. Your margin of error in estimating averages is given to you by the product of t-scores, the standard deviation, and divided by the square root of your sample size. So we just need to rearrange this equation to solve for n. And if we do that, I'll divide t on both sides. I'll flip everything upside down, or take the reciprocal. I'll then multiply by sigma. And I have to pull n out of the square root, so I'll take the square. So this is how I can recover the necessary sample size, except I can't find that t-value because in order to find t-values, you need to use your table, and your t-values depend on your sample size. So you're kind of stuck in a loop, right? You can't know your sample size without knowing your t-value, and you can't know your t-value without knowing your sample size. So what we do is we replace that t-value with the corresponding z-score. All right, so let's figure out all the pieces here. Let's work on that z-score. So go back up to your picture. Let's clear it off a little bit. So if I'm going to have a 90% confidence interval, I have 90% of my area in the middle, which means I have, I shouldn't have erased those. I've got 5% there and a 5% there. And remember, your z-score critical values has areas to the left of z-scores. So if I have 5% here and 90% here, then how much area is to the left of that? I'm looking for the z-score that has 95% of the area to the left of it. And the corresponding z-score is 1.645. So on your tables, it's stuck between 1.64 and 1.65. So we'll just take the middle value there, 1.645. So that's the z-score that matches my scenario, 1.645. I then need to multiply that by the standard deviation of my sample. So that was 5.3. And the desired margin of error, so back to the problem statement, I'm trying to predict the true average NBA player height to within 1 inch. So that's what my margin of error is, 1. And if I do this, if I take that product, oops, I forgot to square it. If I take that product and then square it, I find n needs to be 76.01, which that means that 76 won't cut it. I need to round up and find 77 NBA players that I can take their average height. That will give me a margin of error of 1 inch, or technically a little bit less than 1 inch.